morning and welcome back to the class. In the previous class, I talked about lithium sensors. So, today I will talk about sodium sensor. Okay, let us look at sodium. The sensor would be one which should be able to detect detect 0.3 to 300 millimole of sodium in blood, in human blood, okay? In blood. So, this is one condition. Second condition is should be able to detect within the physiological pH. pH that is 6.6 to 7.8 within this pH range. That is when you are thinking about constructing a sodium ion sensors, this should be in your mind. Okay. Now that the basic ideas are clear to you, you should be able to design. Okay. And finally, sodium should be able to detect preferentially over lithium and potassium. Over lithium and potassium, especially potassium, because sodium and potassium are two very important alkali metals present in our body. So, we have to have a receptor which will bind sodium ion preferentially over potassium, and in manic depression patient usually lithium is given, okay, lithium drugs. So, there will be lithium. So, lithium is a smallest cation and it should be really hydrated in cell in vivo. So, lithium discrimination is easier than potassium. So, here I will give you some examples of very good examples of sodium. Well, one of them I have already given, like this one. Oh, that is why I am getting into problem. Yeah. Okay. As I told you previously, I am putting aromatic as such, and then we can have this nitrogen and 5 ethereal oxygen. If we put 6 ethereal oxygen, that binds preferentially potassium. Okay, so sodium will come here, sodium will be here, and once sodium binds, the lone pair is engaged, is easy. Okay, so when we take it, when it is empty, when the cavity is empty, then there is no fluorescence because of PET. But when sodium is added, then the lone pair is engaged, so PET is blocked and we see a strong fluorescence. Another new, well, this is another again same nitrogen, another system. Okay, so this is I am not writing all of it. There are 5, 1, 2, 3, 4 and 5. Same as this one. This one I am writing in a different way, and then maybe I will forget it. I will write something else. Okay, another one. See, there are numerous way you can have these sensors. It is not necessary that I should give you all of it. Here is one very interesting one. Let me write it with some time. Okay. Writing it is difficult. This is based on calixarenes. Those who are macrocycle, and this is calixarene. And this is interesting. That is why I am writing. Okay. So, I am just writing calixarenes. Okay. Okay. And they are bound. Okay. So, we know that they are bound. Okay. So, these are bound. Which way? I may be wrong, the structure wise, but this is my, okay, maybe I should not write. Okay. So, this is my representation of calixarene. What happened? Calixarene, 4 calixarene had tertiary butyl, which were removed, all were removed, and because all were removed and the oxygen part, all of us remember this, right? Let me draw it. This, you have OH, and OH. All of us remembered this, and this. Okay, this is calix 4 arene, where I am showing there. So, this one is inverted, and the oxygens inverted, and the tertiary butyl groups are removed. They can be removed. I told you that they can be removed with the help of aluminum trichloride and all that. All right. This oxygen, 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 oxygen. I am showing it because it is a new kind of method to detect. This will encourage you to design your own compound. You can go ahead and design it for fun. ethyl ester, 2 were carboxylate, this is 1 3, and what happening to 1 2? 1 2 are drawn this way, double bond O, carboxylate, this, and here is pyrene. Pyrene I am writing because it is very difficult to write so many things here. Pyrene. This is pyrene. So, this pyrene, okay. I am just explaining to you how this is done. All right. Then single bond oxygen, then this, double bond oxygen, then go there, oxygen, and then you have nitrobenzene added, nitrobenzene. Okay. So, it is bound through this and nitrobenzene. This is pyrene and this is nitrobenzene. This is nitrobenzene. Now, what happens when nothing is added? When nothing is added, okay, input is nothing, nil. That time this pyrene is electron rich, pi system, and nitrobenzene is electron poor, because nitrogen is a very strong, nitro group is a very strong electron withdrawing agent. So, this pi is somewhat electron deficient. So, therefore, it has strong attraction for pyrene, and when there is nothing, then pyrene and nitro groups are coming close to each other. Okay, pi stacking, and they are coming close to each other. If they come close to each other, that time pyrene is my fluorophore. So, if I excite my fluorophore, pyrene will be excited, but since nitro group is close by, then there will be PET. There will be PET. So, PET on, fluorescence gone. So, if PET is on, fluorescence is gone. You can remember this, I just made it up. PET on, fluorescence gone. So, no fluorescence. Why no fluorescence? Because it can de-excite through PET. Okay. So, however, when I put sodium ion, specifically sodium ion goes here, inside here. We can draw different color, does not matter. Sodium, which one color I will put? Maybe this one, sodium. No, it did not work. Sodium, how about this? Okay. Sodium. So, sodium when I put, so when sodium I put here as input, then what will happen? Sodium will bind to this oxygen, this. All these oxygens it will bind to this, because they bind to sodium, so therefore, these oxygens will move away, because when you have this bond, when you have bond between two atoms or atom and ion, there must be a definite bond length. That means, if sodium ion is here, oxygen has to be there. So therefore, when I put sodium, these oxygens will move apart. You understanding? And why they will move apart? Because of the property of calixarine. They are quite flexible. You know that they can move apart or come closer. If they move apart very much, they can go down. That we have learned while discussing calixarine. They can go down and up. Down means what? Down means they were like this, so they will come like this. So therefore, in one words, these oxygens will go further apart. If they go further apart, then my pyrene and nitrobenzene are moving away from each other. If they are moving away from each other, there is no bonding between them. Earlier there was some weak bonding between pi poor and pi excess. So PET was possible, all right, but because they move away from each other, so when now I excite pyrene, then no PET. So now PET is gone, fluorescence on. So my PET gone, fluorescence on. As simple as that. So this is based on PET, photoinduced electron transfer. However, we have cleverly designed, or whoever designed it, he has cleverly designed based on the property of calixarines, flexibility. Okay. So this is an excellent idea. That's why I told you that. Otherwise, simply PET sensors you already know. All right. Now I come to potassium. So for potassium also, like sodium, potassium, what likes potassium? Potassium likes a bigger calixarine, a bigger macrocycle, okay, because potassium ion is it will like a bigger 18 membered. It will like a bigger one. It will like a bigger macrocycle. With macrocycle, these are easy to design, but I would like you to design on your own, which is not available in literature, okay, but using the property of the supramolecular synthons we have been discussing for such a long time. So it can be done with this, or in the morning session I forgot this molecule, but now I remember. Sometimes I am getting old and forgetting things. So this is called coumarin. I sat quietly one place and then I remembered. Okay. This is also a coumarin derivative, Me2. Okay. Okay. No, I made a mistake. Oh, coumarin, yeah, that is what I think. This is coumarin. Okay. Oh. Okay. So, this coumarin, this is my coumarin, and it is conjugated all along, conjugated, and then nitrogen, and again that macrocycle. So, nothing great about this, because this is a if you can easily, this is easily found anthracene, anthracyl moiety. So, this is a coumarin, it will give emission at a different position. Coumarin is a, this is a coumarin derivative, this is a coumarin moiety. Coumarin, let me write coumarin. Coumarins are photophysically very important, and they gave the quantum yield very high. So, that is why the coumarins are sometimes used, but it is a tedious, expensive. Anthracene is very easy, it will give fluorescence. So, when these are empty, PET is on, when excite, PET is on. So, therefore, no fluorescence, and when they are occupied, then PET will be blocked, stop, PET is off and fluorescence is on, okay, in both these cases. So, they used another one is cryptand. Okay. Okay, is a cryptand, and here is an aromatic. I do not know, this is not a very useful to have, but they made it because of synthetic difficulties and all that. Okay. This is a benzene here, and that is related to again connected to anthracene. Connected to anthracene. Okay. So, this is also a potassium. When it is empty, when I excite this fluorophore, then from nitrogen, now I remember why this is there. From nitrogen lone pair, this is connected to this aromatic group. So, through the, with the help of the aromatics, electron can be pushed towards anthracene, anthracyl moiety. So, that is why this aromatic group. Okay. And here is also same aromatic group. I think you know how to synthesize this molecule. You can synthesize it, this molecule, by means of stepwise method. Why stepwise? Because only this bridge is different. These two bridges are same, but this is different. So, stepwise method you can make. All right. So, this is also a compound. When this is empty, then from this lone pair through this benzene ring it comes here. So, PET will be on all the way, but when you have a metal here, metal is potassium, then it will be engaged and PET is off, and we will see a strong fluorescence. Okay. and then this one is also known with coumarin. With coumarin, this is also known. With coumarin, this is also known. CF3. These are another coumarin. Okay. Coumarin derivative. This is also coumarin derivative. This is not connected, but this is integrated. That is the difference between two. Okay. Okay. This is the compound, and here also this is a coumarin derivative. When it is empty, even though it is integrated, no fluorescence. But when I put potassium, we see very strong fluorescence. So, that means I get now with many systems where you have either receptor and fluorophore integrated, or receptor and fluorophore connected through spacers of different kind. Okay. In both systems, we see these are all these are mechanism is photo-induced electron transfer. So, this way there are sensors for cesium, sensors for rubidium. We are not bothering and giving you details, but it will be very interesting for you to try and make and design at least on piece of paper. Whether that is synthetically possible, we will discuss later with you, but you can design this receptor and fluorophore. You can take only anthracene, does not matter. With anthracene fluorophore, you choose different receptors for different metal ions. Okay, that will be fun. So, these are alkali metals. Some of them can be used for alkaline earth metal also. You know, the alkaline earth metals, two are very important. One is calcium and other is magnesium. So, these two are present in our body, these are essential, and calcium sensor and magnesium sensors are also available. So, those also we are going to discuss, but they are done on different mechanisms. So, what I am going to do in the next class will be transition metal induced fluorescence. Okay, thank you.